Hello everybody. In the last video, I described a series of steps that are very common in engineering, where we begin with a question about some system of interest, and then in order to answer that question, we build a mathematical model of the system, and then maybe we can apply some analysis to that mathematical model to obtain our answer, but more often than not, we end up resorting to a computer. And so we implement the model in that computer, and then we can run some numerical algorithms, and this gives us the answer to our question. As an example of this, we took the initial value problem. And in the initial value problem, the question is, how is the system going to evolve when we started from some given initial configuration? The model here will be an ordinary differential equation or a partial differential equation, but we're going to stick to ordinary differential equations just because they're much simpler. And then to implement this in the computer, we use a numerical algorithm such as Euler's method that I described last time. So in this video, we're going to see how we now implement Euler's method applied to some ordinary differential equation to solve the initial value problem in a computer and using Python. Let's recall the problem. The system is a simple pendulum with friction. So this is the ordinary differential equation, and these are the initial conditions. And the first step was to put this into vector form. So that meant, first of all, defining a state vector. That state vector, y, consists of the angle and the angular velocity, omega. And we called these y1 and y2. And then the second step would be to take our scalar ordinary differential equation and put that into vector form. And so that meant defining this function f that takes y1 and y2 and returns an array that is y prime. That array, in this case, has as its first element y2, and as its second element will have negative a times y2 minus b times sine of y1. Then the next step would be to implement the numerical method. And that means first that we have to take our time period that goes from 0 to capital T and discretize it or chop it up into equal sized pieces. So we end up with k time steps, and each one has duration h. And then we can implement the numerical method. That this is the pseudocode for it. It starts by initializing the estimate y hat to our given initial condition, and then running a for loop. And in that for loop, we are going to compute y hat at each of the time instances from 1 all the way to capital K. Now, we're using Euler's method. So Euler's method says that the slope between y hat of k and y hat of k plus 1 is going to be this s, and that is going to be estimated using these the function f that we've already derived. So this is Euler's method. Now we're going to go to the code and see how we can implement this algorithm. Here we are in Jupyter Lab on the left. And as I've said already, simulation code tends to follow a pretty set pattern. And so now I'm going to describe the 8 steps of that pattern. It begins with defining the constants of the system. And then if there are any quantities that depend directly on those constants, we can compute them next. Then if there are any auxiliary functions that we're going to need, it's a good place to put them next. Then we are going to allocate the memory for the NumPy arrays that we're going to use to track the result of the simulation. Then we initialize those arrays. And then we do the iteration itself through time. And then once that is done, we can do some analysis, such as, say, computing a performance metric on the result. And then we can create some beautiful plots. So now we are going to implement these 8 steps for the simple pendulum. And on the right here, we have a sort of cheat sheet that's going to help us along. All right, so first with the constants. these are the constants involved. There's the mass of the pendulum, the length of the rod, the friction coefficient, the acceleration of gravity, the amount of time that we're going to simulate, how many time steps we're going to split that into, and then the initial condition, the initial angle and the initial angular speed. So let's put that into the code. I'm going to say mass is equal to 0.5, and I like to record in the code the units of each of the constants. This really helps to avoid lots of bugs that arise because of confusion over units. So I'll say that the mass is in kilograms, then the length is 1, and that is 1 meter. Then the friction coefficient is 0.3, and that is in kilograms per second. Gravitational acceleration is 9.8, as we all know, in meters per second squared. The simulation time is going to be 20 seconds. We're going to split those 20 seconds into 1,000 pieces, and that is unitless. And then the initial angle is pi over 3, and that is in radians. And then the initial angular speed is going to be 0, and that is in radians per second. Okay, very good. Next, the dependent quantities. So these are any quantities that are just applying a formula to the constants that give us those quantities. Examples of those in our system, we have the coefficients of the equations of motion, A and B, and then the duration of the time interval. So, of course, in a course like this, you would not have to know how to derive these. We're providing them to you. So let's just put them into the code. A is equal to C over M, B is equal to G over L, and H is equal to capital T over capital K. Okay, next, auxiliary function. These are any functions that you might need later in the code. In our case, the only function that we need is the state equation. And you remember that the state equation takes as input the state vector and produces another vector, which has 2 elements in this case. So let's implement that. We're going to create a function. We'll just call it f. And it's going to take the state vector as input. And then it's going to return a new vector. Let's just call it s, as we've done before. And s is going to be a NumPy array with 2 elements. So the first one is y2, and the second one is negative a times y2 minus b times the sign of y1. Close the tuple, close the array. Okay, now we need to define y2 and y1. And you remember that that comes from the state vector. The state vector has components y1 and y2. And we're getting the state vector in the input. So all we need to do is unpack that state vector into y1 and y2. There you go. How about A and B? Do we need to pass these in as well? Well, the answer is no, because in Python, any variables or constants that are defined at this high level, like the dependent quantities and the constants, that's called the global scope, are going to be available within functions that are also defined at that level. So in short, A and B are already available for us here. Now you could pass them in if you wanted to. I tend to not pass in constants, but only pass in as arguments to my functions things that are changing in the iteration. Okay, so that's our function f. Next, memory allocation. So we're going to have to allocate memory for our estimate of the state. And I'm going to suggest here that we organize it this way. Create a matrix that is going to have as its first row is going to be y1, the second row is going to be y2, and then it's going to have as many columns as there are time steps. So from the 0th to the kth time step, that means it's going to have k plus 1 columns and 2 rows. So let's allocate that. So I'm going to say y hat is equal to np dot empty, and recall that empty signifies that we are committing ourselves to writing every single value in this array. And the shape of this is going to be 2 by k plus 1. Okay, let's just check the shape of that. Oh, I haven't run anything here. We have to run all of this. And the shape is 2 by 1001. So very good. That's what we expect. Okay, next, initialization. We're going to initialize the first column of this array, that is the initial condition. We're going to set that to the initial angle and the initial angular speed. So let's do that here. The first column, so all rows, first column is going to be equal to, well, first theta naught and then omega naught. Okay, so actually you could have done this. This is just fine. You could also have done this in this way. The first row, first column is theta naught, and y hat, the second row, first column is omega naught. That's just as well. You can do it either way, whichever you prefer. I'm going to leave it this way as we had it before. Okay, that's the initialization. Now we get to the iteration through time. And here is where we are going to fill in all of the remaining columns up to the kth column. And we do that with an iteration through k from 0 to k minus 1. And so we can implement that with 4k in range of capital K. If you'll recall that the range built-in method generates integers from 0 to k minus 1. Okay, so now the first thing that we're going to do here is compute our slope, s, by calling our function f and passing in the kth column of y hat. Then once we have s, we can fill in the k plus 1th column and assign it to the kth column plus h times s. Isn't that nice? So now let's run this. Fingers crossed. Oh, what happened? I didn't say y hat. Obviously. You probably saw that. Okay. Y hat, and now that ran. Very good. Next thing, the analysis. So what might we do here? Well, we can compute the energy. So you remember that the pendulum, as it swings, it's going to dissipate energy, and eventually it's going to come to a standstill. So if we compute the energy through time, we can expect that it's going to be decreasing. That is, the derivative of the energy must be strictly less than 0. And that's something that we can check, and it's a good way of, say, finding bugs. So the energy of the pendulum consists of the potential energy V and the kinetic energy K, and this is the potential energy, and this is the kinetic energy. And of course, that's not something that you need to derive in this course. You're just given the formula, and we're going to implement it now. And notice that it depends on omega, on theta and omega. And theta and omega are now computed and in our y hat matrix. So y hat looks like the first row is theta and the second row is omega. So now let's extract those just so that we have a variable name for it. Theta is going to be y hat, the 0th row, and omega is going to be y hat the first row. And now we can implement this energy function relying on the element-wise operations of NumPy that we've already learned. So with that, it's just very simple to implement. I just say E is equal to m times g times L times 1 minus np.cosine of theta plus 0.5 times m times L squared times omega squared. Okay, very, very simple. I can run that. And the next thing I would do is I would make some plots. I would plot theta, I'd plot omega, I'd plot the energy, maybe make the state space plot of the spiral that I showed before. And here is an example. Here we see through time that theta is sort of wiggling and it decays. The speed goes to 0, and indeed the energy is decaying through time. So in the next video, we're going to learn how to make these plots, and we're going to focus on plotting with Matplotlib. So I'll see you then. Bye-bye.